Hello everyone, welcome to SteamCode. In this video we'll be discussing vectors. So what are vectors? Vectors are objects that have both a magnitude or a length and a direction. So let's look at this visually. We'll represent a vector by an arrow. So it has a magnitude or a length. I'll shorten that to mag. And it also has a direction. I'll shorten that to dir. And so the point that it starts off at is called the initial point, and the point that it ends at is called the terminal point. And so because vectors are only defined by their magnitude and their direction, multiple vectors that have the same magnitude and the same direction could be considered the same vector. So let's look at this on the coordinate axes. This is the y-axis and the x-axis. So a vector that starts at point 0, 0 and extends towards 1, 1 is the same as a vector that starts at 1, 0 and ends at 2, 2, or 2, 1. Sorry about that. Because they both have the same angle from the x-axis, let's call that theta and theta, they both have the same length. So a vector with the same angle and same length somewhere up here is the same as one over here. But something to keep in mind is that the vector has to point in the same direction, because the direction is not independent of the angle or the way that a vector points. So say we have the same vector that is composed of the points 1, 1, and 0, 0, but instead points in the opposite direction. It's not the same vector, but it's still a parallel. While it's still a parallel vector, they point into opposite directions. All right, so now let's talk about vector components. So each vector is composed of components. Each vector must go a certain direction in the x direction and a certain direction in the y direction. And so there are multiple ways to express these components. The first one I'll show you is using these brackets. So the amount that a vector goes in the x direction will be described in this first box, or this first value, and comma the amount it goes in the y direction. And you can add however many directions depending on which level you're working at. So whether you're in 3D, 4D, or 2D. And so this vector would go 1 unit in the x direction and 2 units in the y direction. We'll talk about the second way to express this in the next slide, but this vector would be the same regardless of where it started out. Because as you can see, even if this vector goes 1 direction in the x, or 1 unit in the x direction and 2 units in the y direction, but it starts off in a different location, then it would still be the same vector because it has the same direction and the same magnitude. So if vectors pointing in the opposite direction, so let's extend this just a little bit. If a vector is pointing in the opposite direction, then the vector components would have to take into account that change as well. So let's say -1, -3. Because it goes -1 unit in the x direction and -3 units in the y direction. All right, so now let's talk about combining vectors. So geometrically or graphically, vectors can be combined just by adding up the initial and terminal points. So say we have a vector A and a vector B. What is A plus B? So all you would need to do is add the initial point of the last vector to the final point of the first vector. So I'll draw this on a new graph to make it easier to see. So we have A right here. Add on the initial point from B to the final point of A. Then connect the two final points, and then we have A plus B. Sorry, this is not to scale. Now we have A plus B. And you can also subtract the vector. So say we wanted to have A minus B. Then we'd have A. And think of the minus as A minus or A plus negative B. And so if a vector is negative, that just means you take the components of that vector and make them negative, or you turn the entire vector in the opposite direction. Now we have A, and then we also have B. Imagine B is going in the opposite direction now. Then the vector that connects those 2 points is now the final vector, A minus B. And so vectors also have scalar components, and we hinted at this with the minus sign. And so a vector can be scaled up or scaled down while still pointing in the same direction. So what is 3A? It's a vector that still points in the direction of A, but now it's scaled up 3 times higher. So this entire vector would be considered 3A. Imagine there are 3 vectors that are A, and they're just added together. So A, and A. And so using this concept, we can represent vectors in a different form, known as a different component, or known as scalar components of a vector. So say we have the vector v, which is equal to 1, 1. Then we can also describe this as 1 times I plus 1 times j. Now, what are these i's and j's? So I and j are what's called unit vectors. And unit vectors are vectors that only have a magnitude of 1. And these are special vectors, as you can see from the hat, because they only point in the x or y direction. So I will always point in the x direction, and j will always point in the y direction. And so what we're saying here is we're saying we want to add up. So v is the addition of one unit vector in the x direction, and 1 unit vector in the y direction. So we have 1 unit vector, length of 1, in the x direction, plus 1 unit vector in the y direction with a length of 1. And that adds up to the vector v. And you can also denote vectors with the arrow on top. So now let's move on to some practice problems, now that you have the basic understanding of how vectors work. So let's read the first problem. Find a plus b, 3a minus 2b, the magnitude of b, and the magnitude of b minus a. We haven't introduced this concept of magnitude yet, so let me go over it. The magnitude, well, we've talked about the magnitude. Magnitude is length. And how do you actually find the magnitude of a vector? Well, use that same concept of vector component. So let's just create a vector v, and v is equal to 1, 5. How would you find the magnitude? Well, let's draw this out. So it goes 1 in the x direction, and it goes 5 in the y direction. So as you can see, this is a right triangle. So just use Pythagoreans Theorem. 1 squared plus 5 squared would equal to the magnitude or the length of this vector. And that can be denoted either by absolute value signs or by the double bars. You'll see both in your textbooks or on the internet. Either is valid. And so using this, we can now solve this question. So find a plus b, where a is 1, 3, 1. And as you can see, this is a 3D vector. Vectors can be in whatever degree you want them to be. So this is 1, 3, 1. And b, which is 2, 1, 1. So let's add their components. So a plus b would equal, what's 1 plus 2? That's 3. What's 3 plus 1? That's 4. And what's 1 plus 1? That's 2. Now let's find 3a minus 2b. Let's break this into parts. So what's 3a? 3a would equal to 3 times 1, which is 3. 3 times 3, which is 9. And 3 times 1, which is 3 again. 2b is equal to 2 times 2, which is 4. 2 times 1, which is 2. And 2 times 1, which is 2 again. What's 3a minus 2b? Subtract their components. 3a minus 2b is equal to 3 minus 4, which is negative 1. 9 minus 2, which is 7. And 3 minus 2, which is 1. Let's find the magnitude of b using this Pythagoreans theorem. So the magnitude of b is equal to, well, b goes 2 units in the x direction. The Pythagorean theorem can be extended into the 3D because, as you can see, it would not only work with 2D but also with 3D. So 2 squared, the square root of 2 squared, plus 1 squared, plus 1 squared, and that would equal to the square root of 6. What's the magnitude of b minus a? Well, let's first find b minus a. And b minus a is equal to 2 minus 1, which is 1, 1 minus 3, which is negative 2, and 1 minus 1, which is 0. So the magnitude of b minus a would equal to the square root of 1 squared plus negative 2 squared plus 0 squared. And what's that equal to? That's equal to root 5. All right, so now let's move on to practice problem number 2. So this is more of a physics problem, and you'll probably see questions like this if you're taking physics. But let's read through it and let's draw a picture so we can understand it. So a 100-pound weight hangs from 2 wires. The wires make a 45-degree angle and a 60-degree angle with the weight respectively. So find the tension forces in both wires and the magnitudes of those tensions. So let's draw a picture up here to help us out. So we have the ceiling. We have 2 wires and the weight. So this weight is 100 pounds. We have the 2 wires right here. So one wire makes a 45-degree angle with the x-axis, or with the weight. Another wire makes a 60-degree angle with the weight. And we know that these are tension forces, so those can be represented as vectors. So let's call this tension 1 and tension 2. And we also know, given from the problem, that it has a weight force pulling down of 100 pounds. All right, so let's break these tensions into components. Let's solve for each of those components. So because these are not pointing directly in the x direction or directly in the y direction, we know that they must be some sort of addition of x and y unit vectors. So using our trigonometric knowledge, we know that in the x direction, that would have to equal to the magnitude of this vector, T2, multiplied by cosine of 60 degrees. Now, why is that? Well, because we know that cosine of 60 is equal to whatever this vector is, whatever this component vector is, divided by T2. So cosine of 60 is equal to whatever that is. I'll represent that by a question mark, divided by T2. We'll solve for that question mark. What's that question mark? Multiply both sides by T2, and we end up with T2 cosine of 60. Let's use the same reasoning for the y direction. What's sine of 60? That's question mark over T2. What's that question mark? That question mark would have to equal to T2 sine of 60 degrees. Now let's use the same reasoning for this other wire. In the x direction, well, we know that this is pointing in the other direction from this wire, so we know that this has to be negative. So in the x direction, that would be negative T1 cosine of 45. And then in the y direction, we know that would have to be T1 sine of 45. And remember, we're just using that same reasoning of cosine of 45 is equal to whatever this length is, divided by tangent 1. So in order to solve for that length, multiply both sides by tangent 1. So you have negative tangent 1 cosine of 45. And remember, the reason why this negative is here is because even though these two vectors are parallel, they're pointing in opposite directions. Now let's set up a system of equations and let's solve for both sides. So because this weight is not moving, then we know that the forces have to be equal. And so tangent or tension 1 cosine of 45 would have to equal tension 2 cosine of 60. Remember, these are degrees. Now, why is that? Because tangent 2 cosine 60 is the component of the tangent of the tension 2 wire in the x direction. T1 cosine of 45 is the tension component of this tension force in the x direction of tension 1. And those have to cancel out because this is not moving, this weight is not moving in the x direction. So those have to equal one another. Now in the y direction, the addition of these two vectors has to equal to the weight force pulling down. So let's represent that algebraically. So T1 sine of 45 degrees plus T2 sine of 60 degrees has to equal 100, because remember, it has a weight of 100 pulling down. Now we can just solve for T1 and T2 using these systems of equations. So first, let's find out what cosine of 45 is. So as you remember from your 45, 45, 90 triangles, the ratio of the sides is 1, 1, and root 2. So cosine would equal to 1 over root 2. So tangent 1 over root 2 is equal to, now let's use the same with the 30, 60, 90 triangles. So if this is 30 degrees, this is 90. Then opposite of the 30 is 1. Opposite of the 60 is equal to root 3. Opposite of the 90 is 2. Remember, this is the ratio between these side lengths. So cosine of this is root 3 over 2. So tangent 2, root 3 over 2. Now what's T1 sine of 45? That'll be T1, what's sine of 45? 1 over root 2. T1 over root 2. And then plus T2 sine of 60. What's sine of 60? That's 1 over 2. So T2 over 2 is equal to 100. Now let's solve for T1 and T2 respectively. So we already know that T1 over root 2 is equal to T2 root 3 over 2. So let's replace that value for this. So let's rewrite that equation. That becomes T sub 2 root 3 over 2 plus T sub 2 over 2 is equal to 100. Now multiply both sides by 2. That becomes T sub 2 root 3 plus T sub 2 is equal to 200. Now let's factor out a T sub 2. It becomes T sub 2 times root 3 plus 1 is equal to 200. And then T sub 2, divide both sides by root 3 plus 1. So that becomes T sub 2 is equal to 200 divided by root 3 plus 1. Now we have the magnitude of T sub 2. Now let's find the magnitude of T sub 1. So I know this might look pretty ugly, but let's get through it. So T sub 1 is equal to T sub 2 root 3 times root 2, that's equal to root 6, all over 2. What I'm doing here is just multiplying root 2 by both sides, and that's equal to T sub 2 root 6 over 2. And so what is T sub 2? As you can see, we solved for it up here. So T sub 2 is 200 over root 3 plus 1. So T sub 1 would equal to 200 over root 3 plus 1 times root 6 over 2. Now we have the magnitudes of those two vectors. And now we have the solution to the problem. But we also need to find the actual vector, so let's find this in component form. So we know that T sub 1 is equal to, in the x direction, we have negative T1 cosine 45, so that becomes negative T sub 1 cosine of 45 degrees. And then we also have T sub 1 sine of 45, so T sub 1 sine of 45 degrees. And then T sub 2 is equal to T sub 2 cosine 60 in the x direction. And then T sub 2 sine 60 in the y direction. Now, since we've already solved for T sub 1 and T sub 2, you can leave it in this form and just substitute T sub 2 and T sub 1 into this form right here. All right, so that was a basic overview of vectors. If you have any questions, leave them in the comment section down below. I will try to answer as many as I can. This has been SteamCode. I hope you've enjoyed, I hope you've learned, and I will see you next time.